Thank you so much for the invitation. It's an honor to be with you here today. I'd like to share with you a little bit of our experience. As was mentioned, I think one of the distinguishing characteristics of my group is that we're pretty applied. So we're out there in the field, we're looking at the problems, we're looking at the applications of a lot of the theoretical foundations that we have here. And I think that's a space that we like to live in. So I'll be making some observations about the state of the industry. I'll be making also some comments as to what the opportunities are. I'll also like to give you some, how should I say, minimum of things that you can do today, because sometimes these talks can turn into fear, uncertainty, and doubt, the FUD factor, right? Which is good for selling security type products, but sometimes not so helpful. And then end up with some of the work we're doing in the research side of things. So I'd like to start off by talking about a new normal. Here at MIT, some of you who are closer to the Institute might know, hacking is not a bad word. In fact, it's a good word. It just means something that you're working at a pretty high level of intensity and making some new discoveries. In fact, if you don't know, we have a museum to hacking. These are some of the things that you'll see, some of the great ones that students have done over time, as you move into color. For those Doctor Who fans in the audience, upside down furniture there if you can't see it. This is a good one. For those of you who enjoy video games, this is with the school down the road, right? This is more along the veins of what we're going to be talking about, the top page of the MIT for April Fools. And this is one of the most recent ones. Somebody rigged the green building with lights so that you could walk up to it and play Tetris. Real time. Talk about a big game, right? But one of the distinguishing characteristics in a lot of this work, a lot of the first viruses, was students exploring the boundaries of what could be done, trying to learn, trying to see the possibilities of what these systems were. A lot of the initial work in computing, networking, time sharing, etc., started here at LCS. So that was the spirit of the hack, right? What you see today is more like this. This is a cybersecurity attacks price list from a lot of the well-funded, well-invested, sophisticated, hiring top talent industry in St. Petersburg. Take a look at denial of service attacks, $30 to $70 a day, $1,200 a month. You get a discount if you go in volume. Hacking a Facebook Twitter account, $130. Hacking a Gmail account, $162. This is now products that are being developed. This is an industry that's well organized and that's formulating business cases and going after them globally. Right? So this is a very different scenario that we're looking into. Obviously, the motivation is there's a lot of money. And the advances, once you start to look into this a lot more closely, you see that it doesn't take that much. It takes maybe a couple of years to get to a pretty proficient level. And the attacks, I'm showing this tool right here, their entire suites, and this is not some underground tool, this is something that's readily available. It's called Backtrack for those of you on laptops if you want to look at it. You can simply navigate it, choose operating system, choose type of attack, choose type of compromise that you want to do, and you can launch it, right? So these are things that are available globally. And the penetration and success of many of them, for those of you who follow this industry, will recognize that SQL injection, will recognize that denial of services are pretty commonplace and have been around for a long, long time. Yet if you see the most successful attacks today, those two are still the ones. So there's still tremendous challenges to be addressed. I'd also like to begin here with a conversation on passwords. We all use passwords, and there's a growing awareness within the industry that these are over. And I mention it because most of you are leaders in your corporations, companies, organizations. And this is one of the things to be mindful of. What's coming ahead? Anybody here with more than 100 passwords? One. Another. I have over 300, right? And the reason I have that many is simply because I'm creating what I call air gaps. I do not want common passwords shared across different services. So I'm not one of those that everyone that, every time I join a new service, I say, use my Facebook credentials or use my Gmail credentials. I'm simply creating more and more passwords to try to create isolation between these systems. However, then I have a problem, right, of a large number of passwords. There's been a continuous stream of password compromises into the millions, right, that we've seen throughout time. This one comes from one that was earlier this year. 2 million credentials from users' computers. Here are the top 10 most common. Just blows your mind, right? Right? Top 10, 1, yeah, right? That's obviously not a corporate password, as most of those, most of those are restricted to the 8. But let's talk a little bit about passwords, right? If we take a look at this list here, we'll start to talk about the space of probabilities of a password. And if you take a look at this password list here, you see that many of these come from this magic number of 95, which is uppercase, lowercase, special characters. And if you have problems coming up with 95, you're probably missing the space bar. Now, what does this translate to? If you look at the common password that is required, which is 8, this is a little bit longer, you'll see that for each of those characters, you have 95, right? 95, 95, 95, 95. So if you multiply all of those together, you get a really big, ugly number, right? Which is great. This is what you want. You want it to be hard to guess, right? But if you use some tricks, obviously, take a look at this, right? You have an uppercase, you have a word, and then you have a number. So if you start to match that, you go, well, for the first one, I'm going to try uppercase and lowercase. Then for the rest, I'm only going to try a character, only lowercase. And then for the last part of it, and many of these have to come from the days of, that the corporate password was required for 6 characters, right? And then it increased to 8. And so what do people do? When your password of choice does not meet the length requirement, you add some numbers, right? And so that's where this rule comes from. So the ones at the end, you add numbers. So if you then calculate that number, now you are 237.6 billion, which you can calculate with this laptop in under 2 minutes, right? So if you've gone from 19 days to 2 minutes using some tricks, right? Now, if you look at the hardware and the computing capability that you have today, with 25 GPUs, each of these comes at the cost of about 1,000, so we're not talking millions here. You could go through the entire space of possibilities for the 8-character password in 5.27 hours, right? So this should be a wake-up call. Now, you can say, well, we should move to passphrases, or we should move our password limit, increase it so it gets bigger. Well, it turns out the story gets more complicated, right? Our previous speaker was talking about big data, and here's where big data comes in a big way, but in a negative way. Every single password compromise that gets made gets leaked into the public domain eventually. And so there's this growing list of passwords that is being amassed. And today, without being, again, an underground hacker, you could get your hands in 1 billion passwords. How unique do you think we are when it comes to choosing passwords? It turns out that we're not. We're pretty predictable across the board. So this is the cycle. Instead of trying to crack the password, say you were trying to guess this hash right here, you would start out with a word that you would pull from one of these password lists, hash it, and there's a number of standard algorithms that go from MD5 to the SHA-1 that's used mostly in banking. You compare it to the stolen hash. If you have a match, you're done. Otherwise, you go on to the next password. Using this mechanism, people have been incredibly successful at cracking passwords. I'll show you an example. Here's the one that happened last year. Those of you who use LinkedIn must have seen this. 6.5 million passwords. Within 30 seconds, 20% of them had been cracked, right? And they were using SHA-1, 30%, 2 hours, etc. Now, all of that other infrastructure and machinery of the web comes into place. This is embarrassingly parallel. You can break it up. You can distribute it throughout the world. You can use the hardware. You can use the list. and so on. And now when this is done, this goes back into that password comments, it gets added to the list, and so on. Not only that, we're starting to see a lot more patterns, right? So, first name followed by years, as we said, special characters at the beginning and end. If you're doing princess, you put dollars, signs instead of S's, etc. So, I've said this is very, very easy, but I want to drive the point home and give you a little demonstration here. What I have here is actually a list of passwords that I downloaded last night. Okay, I went to one of these sites where people like to post passwords that they're looking to decrypt, right? And I downloaded this list of 7,000 passwords, right? As you can see, you can't tell what they are because they've been encrypted. Now, I also downloaded a dictionary. Let me make sure I can escape here. And I'm going to use that dictionary. This is the first one. This is the first dictionary that was made available of passwords, the RockU. It was 36 million passwords. Now it seems like not that much. But I'm simply going to run this dictionary against that password list, right? And I'm using a tool, by the way, I should say. I have to say I'm not teaching anyone to hack or crack because that's illegal, right? I'm simply showing this for the educational purposes only. So when I hit return here, that cycle that I illustrated in the slides is going to kick in. So you can see there how within sub-second or a second or two, I got, you can see here, I'll highlight it, close to 2,000 words of the 7,000. It turns out that a lot of the lists are actually less than that 7,000 because a lot of the passwords are repeated. And if I go into the list, you can start to see the passwords there on the side. Now, these are real passwords that somebody's chosen. And if I wanted to, I could contribute. Good, there's nothing weird because sometimes people use passwords that can be offensive, right? These, if I wanted to, I could contribute these back into the password comment. So this is something to be mindful of. There's a lot of technologies there's a lot of companies trying different technologies to address this, biometrics and others. But this is coming down in a big way. And so this is something that it's important to pay attention to. There's a growing surface area as well when it comes to threats. I'm still talking about threats here. We now have more and more devices, over 8 billion cell phones. We have more cell phones than people because there's obviously more phones than those that have subscriptions. And I'm sure you've heard this. How many of your show of hands have heard of the 50 billion devices by 2020? How many of you, another show of hands, think this is unrealistic? Good. I ran an informal survey at home. I said, let's see how many devices do I have at home. It turns out that I have over 25 IPs in the home. And I thought, this seems unreasonable. But I started going around the house. There's all the laptops. There's all the phones. There's all the Kindle readers. There's the media server, printer, home cloud. There are the television, the media devices, game stations, tablets, cameras, clocks, light bulbs, and sure, I'm not a typical user, but still, there's so many devices that are now coming into the home or into our environment. This one I thought it was interesting. This is the latest e-cigarette. It even has Bluetooth integration with your music player. So it's just amazing the kind of stuff that's coming out. But it's more and more devices. And the issue is that all the vulnerabilities, the vectors of attack had not been fully explored, right? You have vulnerabilities being found in everything you can imagine. This is one I like, the smart toilets, right? Why would anybody want to hack your toilet? I don't know. But, when it comes to health scenarios, you can start to think of some possibilities. I'll ask the question, why are they hackable? Any volunteers? I heard whispers. Yeah, there's a business case attached to it. And the other reason is that it's simply very costly. It takes a long, long time to get all of the vulnerabilities out of a technology, be it a device or be it a software stack. MIT had a problem with an activist in an organization in this past year. They performed an attack. MIT has 100,000 nodes. It might interest you to know also that only 30,000 of those nodes are actually known. People know what they actually do. But those 100,000 nodes were taken completely. MIT went dark. And the attack was a flooding attack. And by the way, the servers were transferred to North Korea. It was anonymous if one of the underground groups. But this DNS technology has been around as long as the web has been. And this was a successful attack on an institution that's pretty good at defending itself. It went completely dark, and the servers were transferred to North Korea. The reason I'm saying this is simply to illustrate how long it takes to simply understand all of the vulnerabilities and protect against them. And with this flood of new devices into the market, we're facing big, big problems when it comes to being able to get that technology well protected and well understood. It takes a lot of money, and at this point, I don't think there's been a strong customer pushback on these devices, but that's coming. It happened for software. I can remember Microsoft and around 2001, 2002 actually froze development across the entire campus and moved to strict code reviews. And after that date, the company got a lot more serious. So I suspect the same thing is going to happen when it comes to devices. Other big problems. Any guesses as to how long it takes from the time a vulnerability is identified and a patch is available till those systems are patched in your average organization? It's in the 3 months. It's actually 6 months. Some machines never get patched, simply because, especially in an academic environment or in a research environment, there's configurations that keep them in a certain state and cannot be changed. This is also taking into account that there's a big lag before that vulnerability gets detected. The average intrusion into a network is 2 years before somebody detects it. If you follow the Neiman Marcus Target scandal, they were in there 6 months prior to launching an attack, gathering data, observing what happened on the network, trying to strategize and figure out what the most effective attack could be. It's also no longer, this model no longer works, right? Where you have these barriers and everybody's bringing their devices from the outside. There's at least a couple stories of major government agencies being shut down for a day and up to a week of somebody coming into the organization with an external device, going out on their lunch hour, browsing the web, picking something up, going back inside, plugging that in, and that spreads throughout the network. The other major vulnerability security professionals will tell you about is the user. I think that's not such a great attitude to take, because I think it's also a tremendous opportunity when it comes to your first line of defense. The more you invest on your users' education, the better you will do in dealing with these scenarios. There's a new virtual machine. For those of us who grew up or are old enough to have seen the maturity of the web, we remember these browsers. They were like books. They didn't even have pictures. Netscape 1.1 innovation was to add images to the web. But if you fast forward 2000 to 2004, you're starting to get applications that are similar to what you had in the desktop. You're starting to get interactivity. You're starting to get sessions, much like you did in the desktop. And if you move forward from that, you see companies starting to build in that model and starting to create a successful platform that is interoperable across all operating systems. And after that, of course, you have Chrome and you have many others, and you have a tremendous success, which comes to what I had in that first slide, establishing a new virtual machine that is now running within the browser. If you go to the security workshops for the Department of Defense, today a lot of the focus is on the browser. They have several days of talks simply looking at JavaScript. JavaScript is the language of the browser, is the language of the web, and it is such a successful model that is spreading way beyond the browser. Now you have it on the server as well. I was down in Walmart last week, and I was surprised to see that a lot of their enterprise computing is moving from the server line of distribution to JavaScript-based servers. The technology is called Node.js. And the whys is a separate conversation, but it's a very, very successful model, not just at the server side, not just at the client side, but also now moving into the storage side as well. Some of the new relational databases that are having tremendous success are also based on this interface. So this is a language and a technology that is becoming pervasive throughout the stack, throughout the tiers, and then one that's worth paying attention to. This is simply just showing the success of how much productivity and how much performance you're now within an order of magnitude from the desktop. And if you optimize your code well, you can get same performance as the desktop. So it's as fast as it's going to get. And it's not just on the desktop, it's also moving onto the phone. You can see here some of the benchmarks for phones are now also including the execution of JavaScript, simply because it is such a high performance, or it's so important to have that high performance. The reason for it is the same as it was in the desktop. It is simply too expensive to maintain applications across different operating systems. Your engineering cost and your support costs are just way too high. The more you can put of this technology into the apps, typically they have a thin native Chrome shell, the better you lower your costs are going to be. Now, a lot of the vulnerabilities, I've heard numbers from people in the industry say over 80%, over 90% of the problems we see today come from the browser. A lot of them in the early days had to do with the plugins. If there was a wall of shame, Adobe should be up there. Year after year, quarter after quarter, you have the plugins, you have the vulnerabilities on the Flash player, you have vulnerabilities on Macromedia and that stack, but it's also moved into PDF. And this is why, if you look at your browsers today, the modern browsers, if you're in a current one, when you click on a PDF, it doesn't download to your to your operating system as it did before. The browser has a built-in PDF viewer, simply to address the vulnerabilities that have come from that. But it's a long, long list. Java, the latest version, I run Mac on my personal laptop. I couldn't even load it because the machine was blocking me until Java said, no, it's not ready yet. You can't install it, So a lot of the vulnerabilities are coming in from this side. The other thing I'd like to talk about is also shadow IT. There's a problem within our organizations today across the board of not only external devices, but external applications. I have a friend who runs the largest medical network there is in the United States, over 3 million patients, thousands and thousands of doctors, and he tells me that running his network is analogous to having a car company where employees would come in and would get to make any car they wanted. He said, this is the scenario that I'm living today. He says, he told me, let me tell you a story. I have a doctor who's a superstar, went home, bought a MacBook Pro, came back into the hospital, plugged it in, started to sync his emails, over 100,000 with Gmail, which trigger, of course, for those of you who know, HIPAA regulations, which immediately, sent flags all over the place. He had to have a team of consultants, 60 people, for 3 months, go through every single email that was synced to see if there was a breach of the HIPAA law. He ended up with thousands of those, and you can imagine the types of fines that that triggered in. And he told me, I still do not have control over what people do. Anybody could walk in from the street tomorrow, that's a hospital, because many of the doctors do not just work at the hospital, they also work in their private practice, and start to do that sync. And so this is a big, big problem. Another problem that we see often is just that the budgets are just not there for security. This same network, any guesses as to how many people he had on the security team? 2. That's not a bad guess. It was 4. Deloitte came in and did an audit or an evaluation of where he should be at. It was close to 40 people, right? And of course, he didn't get the 40 people, but at least he had the ammunition to go fight in with the board, and he ended up getting 20-something. And now he can start to get it. Here at MIT, I mentioned 100,000 nodes. Any guesses how big our security team is? It's 3. Right? We're not doing that much better. Imagine all the stuff that happens in here, 3 people, right? So anyway, this is a problem we see often. 80% of users run an authorized application. Of course, it's made easier by the cloud. I'd like to shift in focus at this point. I've talked a lot about what the threats are, what the concerns are. I'd like to talk also about what some of the opportunities are. If you remember nothing else when it comes to how do I look at my organization, remember 800-53. It is the leading standard that is implemented by federal agencies and also in the private sector when it comes to addressing security. It has to do with a well-vetted, investigated set of controls that would address pretty much every single thing you can imagine. If there's one criticism, is that it's way too big, right? It's just grown and grown and grown, started out very small. This is by NIST, but now it's quite big. But it's very thorough, very complete, including the latest revision. Revision 4 has well-documented controls for supply chain. I know many of you here are supply chain. And this is something that it's well worth looking into. Many of the organizations in their first, when they're immature, let's put it this way, in a security, this is what they start with. They start looking at controls, they start doing risk assessment, they start doing a matching, and they start prioritizing and addressing. This is the one thing, as I mentioned, that if you don't look at anything else, you should look at. This is simply some of the gap areas that are being addressed from previous versions. It talks a lot also about how to integrate cybersecurity into your organization so you're not simply putting out fires and dealing with it at a technical level, but also putting it into management and decision-making throughout the corporation. Few organizations have that integration when it comes to making decisions. Having that integration simply makes your life easier, lets you plan better. This is also their risk assessment when it comes to controls. It is also the most widely implemented risk management framework within the industry. The other one you should be aware of is the top, what I call the top 20. These are the top 20 critical security controls. This one is simply saying, and this comes from everybody's 3-letter agency favorite organization, NSA, originally funded by. And this one is simply saying, if you do not have enough money to put in all the controls of 800-53, here are the top 20 that will get you the most bang for your buck. This one is a lot more practical and is simply saying, here is some very specific instructions as to how to address these vulnerabilities. And it goes from 1 to 20, and it also breaks it down by categories. You can see here reconnaissance, getting in, staying in, exploits, etc. It has addresses each of these individually. There's also a list by MITRE. This one is used by the entire industry, which publishes every single vulnerability that exists that appears within the industry on a daily basis. This is the type of subscription that all of the security companies in the space subscribe to and then plug in and make patches and so on available. But this is something that you can subscribe to from your corporation. Ultimately, it's about people, it's about technologies, and it's about processes. If you are, it's like a chain, right? If you're weak on any one of these, you have problems. Also, if you're starting up on this or want to experiment with a research group or an organization, there's no need to spend a fortune. There's a good open source stack that addresses many of the counterpart commercial products that are in the millions of times that are good tools to begin with. A lot of the academic organizations run entirely on these, although even us, we're starting to integrate commercial tools that are not of the open source stack. But this is a good list that will address pretty much everything that you'd want to look at through an organization. Now let me shift at this point. I talked about threats. I talked about opportunities. Let me switch here gears and talk a little bit about our research. One of the problems that we have seen over and over, especially when it comes to computing infrastructure for global corporations, is the ability to understand what's happening in this network. I've seen many scenarios, especially around data, and this is a real case from a company I'm working with, where they said we simply do not have enough times in the 24-hour day to be able to replicate all of our data globally, which means that our engineers are working with dated information. There's also big problems of latency. And so when it comes to adding a new application onto this global network or considering a different alternative, because you will have vendors, most of you come from very successful companies, you will have vendors lined up out your door around the block with solutions, right? How do you vet it? And this is the problem that we've tried to address. We've tried to simulate from the ground up, modeling the network, the resources, the applications, and the impacts of these applications at a global scale to try to determine the utilization that's being done and what needs to be addressed. And so when it comes to adding a new application, when it comes to considering a cybersecurity scenario, what does that look like? And in an integrated, holistic fashion so that you can support decision making. So you can see here a typical event cascade of an application. This is really what it looks like when you open up a file, how much memory, RAID, CPU, what distribution is done throughout the world globally, what servers are impacted, replications, and so on. I'll give you a short little anecdote. One of the first models that was considered was being proposed is the Google model that is used in the data center where you don't replicate anything. You simply leave all the data files where they are. You have a metadata table that simply points to every single file. Sounded like a good solution. All the engineers from both sides were excited. You start to model this globally. You have these rolling workforces throughout the world. First thing you know, Germany wakes up, they pull 2,000 files, they saturate the network, and all of it stops, right? So it's a very useful thinking tool, and as a process itself, simply to discover and integrate everything that's taking place from a computational standpoint within the corporation and put it all into one system that can be viewed. You can see here how all of that replicates to this ugly drawing that represents the many instances of data centers. Is basically a monster, massive agent model where you have communications representing all of the applications and all of the users at a global scale. And you can see here also that once you've gone through that effort, once you have this representative network that's in simulation that you can just turn on and off, you can then start to play what-if scenarios, right? What if we had, in this case, this is the single master throughout the entire world. If you haven't seen the cost of data centers, it costs $1 billion to build a data center, and about every 18 months, you go through the same in energy costs. So if you can eliminate, in this case, they had 13 data centers globally, and if you can go down to one, of course, the savings are great. Here is another one with multiple masters, and you can see that then you can start to explore and start to consider different scenarios at no cost, other than cost in running the simulation, right? We then extended this to many other applications. This platform, one of the latest ones is on malicious attacks, where we're simply looking at an anomaly-based type scenario, where we're looking at the data within the network and trying to address anomalies in the network that way. Some of you might know the number, but for those of you who don't, the virus signatures approach, signature matching approach is a very poor one. The best numbers you'll find is that less than 50% are caught. Some of the companies that are in the space will put it more at below 10%. So really, when you're running a virus scanner, it is not really stopping much. So there's different approaches that are being used to address that. This last section of slides is really just an overview of research projects that we're in. We've been looking at ERP fraud detection with the Department of Defense. We've been looking at fraud detection with the Commonwealth of Massachusetts. Fraud, if you haven't seen it before, is a fascinating space. It doesn't matter what you do. In 6 months, you will be back again at square zero. Why? Because we're smart and we adapt, right? So it's a fascinating space. And you can see here that we've started to build the framework where we take in data sources, and we are then creating all of that, putting all of that into a central repository. We then have a tier of detectors. And here it happens to be fraud, but you could be looking at insider threat or at many other scenarios. Those detectors then raise flags that get ranked and assigned a risk grade, and then presented as visualizations onto subject matter experts. This is work that's going on the way. I threw the slide in simply because I mentioned passwords. We're doing some work where we're creating password firewalls. Basically, think of your username and password as a coordinate on a mathematical plane. We leave openings for the true username and passwords. Everything else gets bounced off. So it's very similar to what you have within a firewall on the network, but this one is focused solely on passwords. We're also looking at decision making and at threat, insider threat. Insider threat is a pretty interesting one. We now have more computing power than we ever did before, and we have more data than we ever had before. So we can start to look at voice. You can get 80% voice to text translation, and then you can kick in all of your data analysis components. You can get spatial movements within the corporation, right? You can get printing habits of people. You can start to get camera movements. And pretty soon, this is, of course, for a very sensitive scenario. Pretty soon, you start to get baselines of behavior, and you can start to investigate the spikes. There's been good cases of insider threats detected simply on printing practices. If you start printing at 5 a.m. or you start printing 4 departments over from where you normally sit, that's a flag, right? And so you start to couple all of this together, and you start to get a pretty good view of what's going on. Same thing with email and so on. So I'll show you to end here. I'll show you a visualization, and then I will also make some closing comments. So I was talking with the security team here, and we were talking about how do we visualize this. We say a lot of the problem of cybersecurity is that's simply not visible. It's not tangible. We can't see it. We know it's out there. We know it's a problem. We know it's challenging. But how do we actually put our hands on it, touch it, see it? So we thought, we sit in an open environment. There's no filter between us and the outside. What if we just plug in the machine and see what happens, right? Capture what comes in and out of there, right? And so that was the premise for the experiment, and I'll show you what we saw. See here. We pull all of this information and we put it, we did address resolution, we did name resolution, geographical resolution, and we created a map with this data. So let me go ahead and open that up. And I could show you the low traffic, but I will show you the full traffic. This is one laptop, nobody was working on it, set on the side, connected to the network. There's an attack from every single country on earth. Not a second goes by without that machine getting hit. And you can see here, the magnitude of the problem. This is one day, one laptop, isolated, connected to the network. MIT has had a very open policy throughout its history, and there's never been any any consideration of changing things. This picture navigated through the administration, and for the first time ever, there's going to be offerings to go behind a firewall. It won't be mandated. You can opt in, of course. But this, I mention it because of the impact of visualization and being able to see this firsthand. I will give you a tour of the world so you can, you can see here that everybody's joining in the party, right? It doesn't matter where you go. The red ones are known problem makers. Obviously, China is well represented, right? But it's not just China. And it's Australia, and you name it, it's there. It starts to rotate the wrong way. Okay, so let me go back to my closing comments. So we talked a lot. I work heavily with data. So let me stay over here so I can read the slide. I work heavily with data. One of the things that I will tell you is that getting data is very hard. I've been on projects where we've gone 3 years and we still have what is equivalent to a handful of Excel spreadsheets. Once we get the data, it takes a long time to clean the data, right? When we have data at high scale, and I'm sure those of you who are working with data in your organizations will agree with this. It takes a long time to get the data in the shape that you want it to be. It takes a long time to understand the data, to know what you can do with it, to understand when we're coming in from the outside into an organization, to understand the workflow, to understand the impacts of this information. So it takes a long time. I also like to mention on what works. It's surprising how effective and how seemingly simple these techniques are. Peer groups. We're looking at cardiologists in Ireland. Most cardiologists charged X for X procedure, right? And all of a sudden, you have this giant spike of somebody who's charging 10 more, right? 10 times more. And you look at it. Doesn't mean it's fraud, but you look at it. There's another case as well of a tax collector who everybody in a single town was getting audited, right? And it turned out he had a strong bias as to the ethnic origin of everybody in that town. And that showed up more than we were looking for. But you started to detect the spike. Peer groups, incredibly powerful technique. Very simple notion, right? More data sets. As I mentioned in the case of insider fraud, you start to look at one data set in isolation, and it doesn't look so different. You start to bring in additional information from the organization. You start to get additional insight. You start to pair external information, weather, events, you name it. You start to see things that you couldn't see otherwise, right? Again, all of this, of course, takes planning, takes time, et cetera, but it's well worth the investment. Data integration, as I mentioned. Many organizations that I know are simply engaged in this process at the moment. Palantir, this is a corporation, the #1 cybersecurity consultant to the NSA, is precisely doing this. They go into your organization, they have a pile of scripts, they have a pile of storage, scalable storage techniques, and they simply take all of those inputs and try to integrate. A lot of organizations were not built, the different components of them were not built to be integrated, right? Somebody said once before, we didn't know we were all writing the same program, right? So these data flows, a lot of data is tied also to power organizationally. What if I let go of this data, right? I'm no longer going to be the keeper of it, or things along these lines, right? And this is a big problem. I was trying to sign up my son for tennis this weekend. My town has 7 logins in different systems within the school. There's the lunch money system, there's the athletic system, there is the town system that somehow is connected to the school. Then there's the school, and depending on what age and what grade you're in, you fall onto different ones. It took me and my wife 2 hours to try to get him signed up for tennis, right? Imagine doing analytics on this data set, right? It'd be a nightmare, right? So anyway, those are opportunities. And the last thing that I'll mention is, take a look at those standards from a cybersecurity perspective, see where you are, see what the opportunities are, and big data is the other opportunity. I'm sure I don't need to tell you this. It's in the process, as the previous speaker covered it, but there's a tremendous amount of opportunities when it comes to looking at data from the cyber security perspective as well. And so with that, I'll stop. Yeah.